Okay, so we're doing 2.4, and then we'll go back and do 2.3. Okay, so we're doing the precise definition of a limit. I'm going to go back through our last example and then more examples. Well, a reminder of the definition, then the example we left off on. So when you have the limit of x going to a, f of x equal to L, given epsilon greater than 0, there exists delta greater than 0. Oh yeah, and someone asked, is it okay to watch the recording later? That's totally cool. If you just want to watch it now, we're here. But I should have it posted by tomorrow. All right, some epsilon greater than 0. There's a delta greater than 0, such that if the distance between x and a is less than delta, then the distance between f of x and L will be less than epsilon. And then we try to do one of these. So we tried to prove it was limit as x goes to 2 of 3x minus 1 equals, so if you put 2 here, 3 times 2 is 6, 6 minus 1 will be 5, so we're going to prove that the output will be 5. And I have 3 steps to this. So the first step is just remind yourself of this definition. Okay, epsilon greater than 0, there's a delta greater than 0, such that when the distance between x and 2 is less than delta, we're going to get the distance between 3x minus 1 and 5 less than epsilon. We'll just call this f of x. Cool. So these are exciting for me, but I don't really plan to put them on a test. You will have some homework on this though for practice. We've got this part. You do some scratch work to find a delta. And you work backwards from f of x minus L. Let's see, look at this. Epsilon. In our case, f of x would be 3x minus 1 minus 5. We got to 3x minus 6, absolute value. Factor out of 3. The absolute value of 3 is 3, so we can bring out that positive 3. And then you were trying to have x minus 2 less than some delta. You got an x minus 2 right here. So the thing we want was f of x minus L less than epsilon. Okay, so I've gotten the absolute value of x minus 2 less than epsilon over 3. And we're here, absolute value of x minus 2 less than delta, so let delta equal epsilon over 3. And then you can write the proof. Proof. Given epsilon greater than 0, there exists delta equal to epsilon over 3. Such that if the difference between x and 2 was less than delta, then when you do these, you do actually usually leave all of your scratch work sort of like on a test, and then you write your proof and just show a little bit of that scratch work in the proof. So absolute value of f of x minus L, f of x minus 5 is equal to, let's jump to here. Well, let's put in the function actually. X minus 1 absolute value x minus 2. So from here to here was all of our scratch work. And then you have the absolute value of x minus 2 less than epsilon over 3. So this side is less than 3 times epsilon over 3. Those 3's reduced to 1, and epsilon is left. So I got the difference between f of x and L dot 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 less than epsilon, and you're done. Some proofs end with a little black square, or some people like to put QED. I like a little square. Next one, we want to prove. Okay, the limit as x goes to 4 of x squared so x is getting closer and closer to 4, which makes x squared, the limit for x squared, equal to, what do you guys guess? Somebody? Type it. X is getting closer to 4, so x squared is getting close to 4 squared. 60. Okay, start with some of the definition for the limit, or the definition for the limit, but make it specific to this problem. So given epsilon greater than 0, there exists delta greater than 0. The distance between x and 4 is less than delta, then the difference between x squared and 16 is less than epsilon. X squared and 16 less than epsilon. Okay, this delta will be a little tricky, but we'll do another problem like this one. So hopefully it'll make sense. But what we'll do is start with some scratch work, start with x squared minus 16. So absolute value of x minus L, absolute value of x squared minus 16. We're trying to get this less than epsilon, but let's write this as a difference of squares. Oh no. Yeah, x squared and 4 squared. So x minus 4 times x plus 4. Okay, I'm going to write this as the absolute value of x minus 4 times the absolute value of x plus 4. And pause really fast and look up here where you've got absolute value of x minus 4 less than delta. So we're trying to work with this part. Except your delta can't have any variables in it, so no x values for some delta. It's going to be like a number. Anyway, we'll put bounds on x minus 4. Or bound x minus, the absolute value of x minus 4. Someone's like, bind. Anyway. So the idea is x is going to 4, assume. You're at least one space away, so you're from 3 to 5. 3 less than x less than 5. Then the absolute value of x minus 4. This is called the Triangle Inequality. Absolute value of x minus z. Oh, I've got a plus. Oops. I circled the wrong part. This was the part, and this needs bounds. Yeah, this one's the distance between x and 4, which we had. This part's new. Okay, so x is getting close to 4, which means we're probably between 3 and 5. And so if the most x will be is 5, absolute value of x minus plus 4 is what we're trying to put bounds on. Absolute value of x add absolute value of 4. And then let's say that you do have 5 right here. So let's take less than or equal to 5 plus 4. So less, which is 9. Okay. Okay, so for absolute value of x plus 4, we've put some bounds on it. We want this, all of this less than epsilon. Let me make sure I got this clear. Or this would be less than or equal to absolute value of x minus 4. And for this one, we've got less than or equal to 9. Okay, there we go. That's what I was looking for. So all this will be less than epsilon as long as the absolute value of x minus 4. Let's see. I put is less than epsilon over 9. So you might be thinking that this will be the delta, so that when you have the distance between x and 4 less than your delta, But you also had this bound over here, which was a distance of 1. So you choose the minimum of 1 and epsilon over 9. Again, 1 comes from your bounds, and epsilon over 9 is from doing this like scratch work. Let's write the proof. Okay, so we start given epsilon greater than 0. There exists delta equal to the min of 1 and epsilon over 9. Such that if the distance between x and 4 is less than delta, then distance between f of x and 16. And again, this is where you put a little bit of your scratch work, but not all of it, because you usually just leave that stuff on your page. Is x squared plus 16. Let's go ahead and jump to this part. And from here to here, we had that bound of 1. And then I put it in the wrong spot. There we go. And then the distance between x and 4 is less than delta. Delta could be epsilon over 9. Let's put in epsilon over 9. So you get your distance between f of x and L less than epsilon, and you're done. Last one, and then let's go to 2.3. Limit x goes to 3 of x squared plus x plus 4. So let's pretend x equals 3, and you put in 3 and square it to get 9, add 3 more, 10, 11, 12, 13, 14, 15, 16. So this limit should be 16. Oh, hang on, something went wrong. 3 squared is 9. This is a minus sign, that's why. It didn't match my problem. So it's the limit of x squared plus x minus 4. When you put in a 3, 9 plus 3 minus 4. 9 squared is 9 plus 3 minus 4 equals 8. All right, so let's do number 1. Epsilon greater than 0. There exists delta greater than 0. Such that your distance between x and 3 less than delta. Then the distance between f of x and L less than epsilon. Cool. Let's find delta. So we'll take this and do some scratch work. We're trying to get the difference between f of x and L less than epsilon. That's the value x squared minus 4 minus 12. Let's see, it's, you factor this and get x plus 4 times x minus 3. And then we can have the absolute value of x plus 4 times the absolute value of x minus 3. And then something right here, x minus 3. So this part's just going to sit there. I need that part. I want bounds on this stuff, x, the absolute value of x plus 4. So bound. So the book says it's reasonable to say you're 1 unit within this number. So we're going to go have x between 2 and 4. Okay, and then we're trying to get the absolute value of x plus 4 bounded. Okay, so the most x could be is 4, so we'll put in absolute value of 4 plus the absolute value of 4. Which is 4. So this is less than epsilon, provided the absolute value of x plus 4 is less than epsilon over 8. Let's do this. Let's try this better. It's the same stuff. I'm just going to make it clear. So this part will be less than, and I'm going to put an extra. So this is less than or equal to 8 absolute x minus 3 less than epsilon. If this is less than epsilon over 8. Yeah. X minus 3 less than epsilon over 8. That's it. And again, you had that possible delta of 1 or this guy, epsilon over 8. And then we can do a proof. Okay, given epsilon greater than 0. That's how they always start. There exists delta equal to the minimum of 1 and epsilon over 8. Such that if the distance between x and 3 is less than delta, then the distance between f of x and 8 equals, put in f of x, what is it, x squared plus x. Okay, usually you leave your scratch work, so we're just going to jump to the part where we have absolute value of x plus 4 times the absolute value of x minus 3. Put a bound on the absolute value of x plus 4. And let's multiply by x minus 3. Absolute value of x minus 3 is less than delta, which could be 1 or epsilon over 8. Put in less than 8 times epsilon over 8. The 8 over 8 reduces to 1, and you've got epsilon. So you got your difference between f of x and L less than epsilon, and then you're done. So these proofs would be something you do if you took math classes past 100. There's a 108, which is an introduction to proofs. And then if you took math 130, you would do this most of the time. I just wanted to show it to you and give you some practice with it. But for the most part, we're going to jump back to learning tricks to find limits and just working with our functions to find limits, not actually doing proofs. All right. 2.3. So I guess what I'm trying to say is this stuff might look hard, but it's not a big focus in this class. It's, okay, this is for limit. Oh, I forgot about infinite limits. Okay, I just found a little extra side note. Let's pause. Before we get to this section, I do want to introduce the definition for an infinite limit and remind you again, this stuff might be on your homework. It won't be on the test. Okay, infinite limits. All right, you've got a limit as x goes to a from the right. Of f of x will have equal to positive infinity. Means given m greater than 0, and m is a very large number, so what my teacher did is wrote given m, which means much, much greater than 0, a very, very large number, much greater than 0. There exists a delta. Greater than 0. Such that let's see, x is going to a on the right. So if a is less than x, less than a plus delta, we have f of x greater than m. So we're going to draw this. We'll have an example function. We'll put a right here and an asymptote. This is going to go to positive infinity as x approaches a. So I'm going to come up and grow really quickly. And then this side too is going up to positive infinity as x gets closer to a. F of x goes this way. Given some m much greater than 0, so some value m like this, there exists a delta greater than 0. Put delta, this is a plus delta, such that if x is between a and delta, when x is somewhere between here and here, then f of x is greater than m. So this output right here goes past that part right there. Let's say x is this guy. F of x would be here at some value greater than m. And that's for any m, so m can keep going up or down or anywhere it wants. You'll always have some f of x larger than that number. So it's always up to positive infinity. Let's do the limit on the left. So as x limit x goes to a, right from the left, f of x equals infinity is given m much greater than 0. There is a delta greater than 0. Such that if a minus delta is less than x less than a, then f of x is greater than m. So this time you're going to a on the left. So delta is still some positive number, but you do a minus delta, brings you to here at a minus delta. X values between a minus delta and a. This part, you can find an f of x greater than m. This guy, x1, we'll call this x2. x2 has an output right here, larger than that number m. And again, m can be any number, so you can push this higher and higher, and then you can find some value of your function greater than that. And we're done with this section. Let's go back to some fun stuff. 2.3. This stuff's cool. Limit laws. Okay, we're going to assume the limit as x goes to a of f of x exists and equals L. And let the limit x goes to a of g of x also exists. We're going to call it some number r. And c is also a number. C is a constant. First rule, number 1, is sum and difference. The limit as x goes to a of f of x plus g of x is equal to the limit of x goes to a of f of x plus the limit as x goes to a of g of x. It's also true if you have f of x minus g of x, you can do limit of f of x minus the limit of g of x. Number 2, constant multiple rule. the limit as x goes to a of c times f of x. So you can have the c times the limit as x goes to a of f of x. Next is a product. Well, actually, I'm going to put c times l, and this would be r plus or minus l, and product. The limit as x goes to a of f of x times g of x. Is the limit as x go to a of f of x times the limit as x goes to a of g of x. And we had this equal to L, this is equal to R, L times R. Quotient rule, so the limit as x goes to a of f of x over g of x. Okay, the limit as x goes to a of f of x over the limit as x goes to a of g of x. Limit x goes to a of x over limit x goes to a g of x over r. And you don't divide by 0, so just note that r does not equal 0. Number 5. Power rule. I'm just going to put, power rule. Sounds cool. Power. The limit as x goes to a, see, of f of x to the n is the limit as x goes to a of f of x with the power n. Some number L with the power n. And limit of a constant. So these ones now are kind of like for specific functions. So number 6 of a constant. So if you take the limit as x goes to a of some number c, it equals c. Okay, I have the limit as x goes to 8 of 5. It equals 5. So you've got your function f of x equals 5. So x is any number, but f of x has to be 5. So that's the line that goes through 5, and it's slack. So that's your function f of x equal to 5, and then you're approaching 8. As x goes to 8, f of x goes to 5. And as x goes to 8 this way, f of x goes to 5. That's your limit. Where are we? Number 7. Linear function. We have f of x equals x. Limit x goes to a of x equals a. We'll draw a picture. You've got your x values here. The line f of x equals x has a slope of 1 and an inverse, and it goes to the origin. So 0, 0, up 1 over 1. And you're approaching a. So as x goes to a, f of x goes to a. As x goes to a on the right side, f of x is approaching a on the right side. I think this is the last rule. So the root rule is it's the limit of the nth root of f of x as x goes to a. Okay, here's the nth root of the limit as x goes to a of f of x. And then I just put a note that our class works with real numbers. We don't have complex numbers as outputs of our function. So we're just not using complex numbers in this class. So when you take an even root of a negative number, it's fine, but of an, what am I trying to say? This is an nth root, by the way. So it can be even or odd. Odd is fine. If n is even, this can't be negative. So if n is an even number, we need this limit to be a positive number. Greater than or equal to 0. If the limit is x goes to a equals 0, then you're taking the nth root of 0, which is 0. What am I trying to say? Any positive number, nth root of a positive number, you're still in the real numbers. It's just that if f of x, so equals, we're just putting in some negative number here. Like, clear 1 is -1. And we need n to be even, but let's say n is odd really fast and see what the problem is. So n is 3. Oh, n is even, then this is positive. If this is even, then positive. We've got a negative number when n is even. This is 2. We have something like the square root of -1, which is the imagined number, which is the complex number I. So this is what I'm trying to say is we don't want any negative numbers underneath even roots. So this is why a little note on the side. Let's call it good. So examples next time. And